Welcome back. Another example. Consider the vector space of all polynomials in variable t of degree less equals 2. That's what the 2 signifies. Suppose v1 equals t squared plus 2t plus 1. v2 is t squared plus 2. Is p2 equal span of these two vectors? That is, can every polynomial of degree 2 or less be written as a linear combination of v1 and v2? Let's check. Suppose v be any arbitrary polynomial from p2, that is a t squared plus b t plus c. We need to check whether v is a linear combination of v1 and v2. Suppose v is a linear combination of v1 and v2. That is, a t squared plus bt plus c is a1 t squared plus 2t plus 1, that's v1, t squared plus 2, that's v2. Okay, so notice combining a1 t squared, a2 t squared. So a1 plus a2 t squared. 2a1 plus nothing, 2a1 t. a1 plus 2a2, that's a constant term. That has to be equal to this. What does this say? You have a linear system. This a equals a1 plus a2. This b is 2a1. And this c is a1 plus 2a2. Which gives you an augmented matrix here. 1, 1a, 1, 1a, 2a1, 2, 0b, and 1, 2c. All right. Which tells us what? We now start doing row operations to get 0 below the 1. Negative 2 row 1 plus row 2 is the new row 2. And negative row 1 plus row 3 is the new row 3. So you're getting zeros here and things change here. Now notice I want a 1 over here. I can interchange row 2 and row 3. That's a typo. It should be row 3 and row 2 are interchanged. Once you get that, this should be negative a plus c, mind you. That goes here. Okay, negative a plus c, not multiplication. Too many typos here. Anyhow, you do this and you got a 0 here. Notice that's a problem. The last entry need not be 0. That is, you see, you can find ABC so that the last entry is not 0. That gets you an inconsistent system. For example, suppose A and C were 0 and B is 1. Then the vector V equals T cannot be written as a linear combination. So where did this vector T come from? AC0, B equals 1. So AC0, B equals 1. So that's the vector V. We cannot have it. We cannot have it. All right, because that would fetch me a 1 here and 0 here. So that would be inconsistent. So P2 is not a span of V1 and V2. Consider the homogeneous linear system, AX equals 0. So that is my A, coefficient matrix. We have seen in an earlier lesson that the solution set of a homogeneous system is a subspace. In this case, N is R, right? It's a 4 by 4 matrix. You're going to multiply by a 4 vector. That's why it's column space of dimension 4. So suppose consider the augmented matrix AX equals 0, right? So augmented matrix, so that's your coefficient matrix, that's the right hand side. We are trying to reduce it. So we already have a 1 here, get zeros here using row operations. All right, turned out I got zeros here as well. Now I have a 1 here, I can get zeros below it. When you do that, you get zeros everywhere. So you are done with the row echelon form. Okay. And this is in fact reduced row echelon form. You see, that's a leading one and there is 0 above and below. That's a leading one and 0 below. This is not a leading one, so I am not required to get a 0 here. In fact, if I do, I will lose this 0. So this is not only just a row echelon form, it is reduced row echelon form. So this is reduced row echelon form. I'm getting back my variables in here. And notice 0 equals 0, 0 equals 0. This means I have infinitely many solutions. I got x1, x2, x1 plus x2 plus 2x4 equals 0. And here I have x3 minus x4 equals 0. So that is x3 is x4 and x1 is this expression. So you see, x4 can be any real number. So can x2. Right? So you have any solution to the given original homogeneous system. X4 can be any real number, x2 can be any real number, x3 equals x4, and x1 equals negative 2x2 plus 2x minus 2x4. So look at this. We can separate it out. You see, I'll keep the x2 part aside and the x4 part aside. All right. So this set and this vector and this vector put together in a set, they span every solution. So the vector space of the solution set is spanned by these two vectors. Okay, it's an amazing setup. Which brings us to our close. Here are the homework problems from the textbook. Enjoy.